In 1969, we were able to send somebody to the moon. 1969.
Why have we not gone back to the moon in 50 years?
The train is like down to nothing. They forgot how to do it.
What would it take to make an honest attempt at lunar colonization?
So I think space colonization, even though I'm all for it, is going to be longer term than we thought.
Imagine stumbling upon an oasis in the most unexpected of places, not on Earth, but on the Moon. Recent missions armed with cutting-edge remote sensing technologies, like NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1 spacecraft, have done just that. They've uncovered water ice in the permanently shadowed craters at the Moon's poles, regions forever hidden from the Sun's glare. This discovery is not just about finding water. It's about uncovering a potential lifeline that could redefine future lunar exploration and colonization.
First of all, we have to leave the Earth. The Earth in 5 billion years will be destroyed. That's a law of physics.
The significance of finding water ice on the Moon cannot be overstated. Water is essential for life as we know it, offering hydration for astronauts and the possibility of extracting oxygen for breathable air. But the implications stretch even further. Think about rocket fuel. Hydrogen and oxygen derived from water are powerful propellants. By mining and processing this lunar ice, we could drastically cut the costs of space exploration, making more sustainable and longer missions a reality.
Climate change will make Earth a living hell. So there's a chance we could terraform Mars. You turn something that's not like Earth into something that's like Earth.
Moreover, this water could be a game changer for building habitats on the Moon, providing materials to shield astronauts from cosmic and solar radiation when combined with lunar regolith. But how much water are we talking about? The permanently shadowed regions might hold millions of tons of water ice. Yet, accessing this treasure trove won't be easy. The depth, purity, and the frigid, dark conditions of these craters pose significant challenges for any robotic mission aiming to tap into this resource. This discovery isn't just about practical applications. It's a window into the Moon's geological history and the evolution of our solar system. By studying the isotopic composition of this ice, scientists can trace its origins, whether it came from comets, asteroids, or the solar wind. This knowledge could provide insights into how water came to Earth and the Moon, deepening our understanding of our place in the cosmos. For a terrestrial comparison, consider Antarctica's dry valleys, some of the driest and coldest places on Earth. Despite their arid conditions, these valleys harbor water ice, preserved in permafrost and shadowed nooks much like the Moon's poles. Studying these earthly analogues helps us understand the potential for life in extreme conditions, the stability of water in shadowed environments, and how we might utilize in situ resources on other worlds. The discovery of water ice on the Moon is a reminder of the surprises our universe holds. It challenges us to rethink our approach to space exploration, emphasizing sustainability and the clever use of off-Earth resources. As we prepare for future missions, this lunar oasis beckons, promising not just survival, but a stepping stone to the wider cosmos. Have you ever gazed up at the night sky and wondered if there's more to the Moon than meets the eye? Among the many celestial mysteries, the Moon holds a special place in human curiosity, sparking a blend of scientific inquiry and imaginative theories. One such fascination revolves around its perfect tidal locking with Earth, a synchrony so precise that it has fueled conspiracies of intentional design. Is it possible that this alignment is not just a stroke of cosmic luck, but a deliberate act by advanced civilizations, or even extraterrestrial beings? Let's dive deeper. Tidal locking, a gravitational dance that results in one face of the Moon always pointing toward Earth, is often cited as too perfect to be natural. This phenomenon occurs because the gravitational pull of Earth exerts a torque on the Moon, gradually slowing its rotation until its orbital and rotational periods match. But rather than pointing to alien architects, this is a natural outcome of celestial mechanics, a common occurrence not just in our Earth-Moon system but across many moons in the solar system. Every major moon of Jupiter and Saturn, for instance, shares this trait, highlighting its naturalness rather than suggesting otherworldly intervention. But the mysteries don't end there. The Moon has also been the center of theories about alien bases hidden within its craters, spurred by anomalous photographic evidence and peculiar lunar phenomena. Strange structures, lights, and transient lunar phenomena have been interpreted by some as signs of extraterrestrial activity. However, a closer look at these anomalies often reveals natural explanations, such as meteorite impacts, lunar seismic activity, or the simple trickery of pareidolia, where our brains create familiar patterns from random shapes. The intrigue around the Moon's features isn't isolated. Similar speculation surrounds Phobos, one of Mars's moons, whose odd orbit and shape have led to theories about its artificial origins. This fascination with celestial bodies and their anomalies taps into a long-standing human tradition of storytelling, where the mysteries of the cosmos fuel our imagination and drive us to weave intricate narratives around the stars and planets, much like ancient civilizations did with their myths. In exploring these theories and the natural phenomena that explain them, we continue the timeless quest to understand our place in the universe, blurring the lines between scientific discovery and the boundless realm of human imagination. Ever pondered how our moon came to be? The story of its origin is not just a tale of cosmic events, but a narrative that intertwines with the very fabric of our solar system's history. Scientists have spun theories, each unraveling a part of this celestial mystery, offering a glimpse into the dynamic processes that shaped not only the Moon, but Earth itself. Among the contenders, the giant impact hypothesis, capture theory, and binary accretion each paint a unique picture of lunar genesis. Imagine, if you will, a cosmos where colossal impacts were the norm. The giant impact hypothesis takes center stage in this drama, proposing a scenario where the early Earth, in its youthful vigor, collided with a Mars-sized entity affectionately dubbed Theia. The aftermath of this titanic clash? Debris scattered far and wide, eventually coalescing to birth the Moon. This theory isn't just a favorite because of its dramatic flair, it's backed by compelling evidence. The chemical signatures of Earth and its satellite are eerily similar, particularly their oxygen isotopes, hinting at a shared origin. Computer simulations add weight to this argument, showing that such catastrophic events were likely in the solar system's chaotic youth, capable of creating a debris disk from which the Moon could emerge. Yet not all tales are of violent beginnings. Enter the capture theory, a narrative of cosmic serendipity where the Moon, once a nomadic celestial body, was ensnared by Earth's gravitational embrace. Romantic as it may sound, this theory faces challenges, particularly when it comes to the striking compositional similarities between Earth and its constant companion. If the Moon hailed from a distant part of the solar system, why then do they share such a remarkable isotopic resemblance? Then there's the tale of binary accretion, suggesting Earth and Moon were born together from the same stellar nursery, growing side by side like siblings. This theory attempts to explain their compositional kinship, but stumbles over the intricacies of angular momentum and the peculiarities of the Moon's smaller core compared to Earth's. Our lunar companion's origin story is unique, not just in the context of our solar system, but in the grand tapestry of the cosmos. While many moons of Jupiter and Saturn are thought to have formed from the planet's surrounding gas and dust, the Moon's genesis seems to follow a different script. And as our understanding deepens, new theories emerge, like the synestia theory, which posits the Moon was born from a vaporized rock donut, challenging and refining our perceptions of how celestial bodies come into being. The journey to unravel the Moon's mysteries is a testament to human curiosity, a drive to understand our place in the universe through the lens of our closest celestial neighbor. As we gaze upon its surface, lit by the sun or softly glowing in the night sky, we're reminded of the cosmic ballet that brought it into existence, a dance of matter, energy, and time that continues to captivate and inspire.
It really is. Oh, geez, that's great. Is the lighting halfway decent? Yes, indeed. They've got the flag up now, and you can see the stars and stripes on the lunar system.
Was there ever a moment on the Moon where either one of you were just a little bit spellbound by what was going on?
About 2.5 hours.
Once upon a time, nearly 4.5 billion years ago, our solar system was a place of chaos and creation. Amongst the swirling debris and cosmic dance, a story unfolded. The birth of Earth's moon, a tale not of gentle beginnings, but of cataclysmic collisions.
It's called the giant impact theory.
The theory states that a Mars-sized body struck the young Earth, and the moon formed from the debris disk around the planet.
In this cosmic ballet, Earth was young and unrecognizable, a burgeoning planet in the vastness of space. The stage was set for a dramatic event, one that would shape the destiny of our planet and give rise to our beloved moon. The key player in this story was Theia, named after a mythical Greek titan. Theia wasn't just any cosmic entity, it was massive, almost the size of Mars, and it was on a collision course with Earth. Imagine the unimaginable. Theia, with its immense size and speed, crashed into Earth with such force that it was more than just a mere impact. It was an event of cosmic proportions, a spectacle of destruction and creation intertwined. The collision was so intense that it tore chunks off our planet, sending a maelstrom of molten rock and vaporized debris hurtling into the space around Earth. From this chaos, something remarkable happened. The debris, the remnants of this violent encounter, didn't just drift away into space. Instead, they began a dance of their own, swirling and coalescing under the force of gravity. Over time, this cosmic debris, born of fire and fury, came together to form a new celestial body, our moon.
The Earth and the moon are actually like identical twins. That means that the Earth and moon are made from the same materials.
This story of the moon's birth was not always known. For a long time, humans gazed at the moon, weaving tales and myths, wondering about its origins. It was not until the late 1960s and early 1970s, with the Apollo missions, that our understanding of the moon's true origins was revolutionized. Astronauts journeyed to the moon, not just as explorers, but as detectives of the cosmos.
You're now national heroes. What are your initial feelings about being heroes?
Probably get an answer to that question. Might have to spend as long preparing as we had to prepare for Apollo 11.
They returned with precious cargo, lunar samples, weighing a total of 842 pounds. These rocks were silent witnesses to the moon's fiery birth. They revealed secrets that previous theories couldn't unveil. The rocks showed signs of having been part of a molten world, an ocean of magma, which pointed to an origin story of great energy and impact. They were like pieces of a puzzle, fitting perfectly into the theory of a massive collision leading to the moon's creation. In the grand tale of the moon's origins, the evidence gathered from the moon itself plays a starring role, revealing a story of unity and separation between the Earth and its satellite. The clues were hidden in the very rocks of the moon, waiting to be uncovered. When astronauts from the Apollo missions brought back samples of the moon's basaltic rocks, scientists made a fascinating discovery. These rocks, formed deep within the moon's mantle, bore a striking resemblance to the basaltic rocks from Earth's own mantle. It was like finding pieces from two different puzzles that matched perfectly. But it wasn't just the rock's appearance that was similar. It went deeper than that. The oxygen isotopes and other elements within these rocks were almost identical to those in Earth rocks. This was no coincidence.
The genetic code of planets is written in the isotopes of the elements. All of the planets are made from different materials, so they all have different isotopes. They all have their own genetic code.
It was a clear sign that the moon and Earth were once part of the same whole. But the story doesn't end there. Meteorites added another layer of evidence. The lunar meteorites, unlike the samples collected by the Apollo astronauts from a few specific sites, provided a broader perspective. These space-traveling rocks, flung from various locations on the moon and eventually landing on Earth, echoed the same historical account of the moon's origins. Moreover, meteorites originating from asteroids served as cosmic timestamps, helping confirm the timeline of the moon's dramatic formation. The plot thickens with more recent studies. Scientists, like detectives with a magnifying glass, analyzed the light reflecting off the moon's surface. What they found was telling. The surface was abundant in Anorthosite, a type of igneous rock that forms and floats atop a sea of magma. This discovery was crucial. It suggested that the moon, in its infancy, was not a solid sphere, but a celestial body enveloped in a deep, extensive ocean of molten rock. This magma ocean, potentially hundreds to thousands of kilometers deep, was a testament to the high-energy impact that birthed the moon. This compilation of evidence from lunar rocks, meteorites, and surface analysis weaves a compelling narrative. It tells of a past marked by a cataclysmic event, powerful enough to break off a part of Earth and create a new entity in space. The moon, as we see it today, serene and unchanging in the night sky, carries the scars of its turbulent beginnings, a mute reminder of its shared history with Earth. In the vast expanse of space, the moon hangs like a silent witness to the ancient history of our solar system. This celestial body, so familiar and yet so mysterious, holds within its craters and plains the secrets of a past event of cosmic significance. The story of the moon is not just a tale of its existence, but a narrative of lunar archaeology, where scientists, much like detectives, unravel the mysteries of its formation and evolution. The moon, compared to Earth, is like an untouched crime scene. Earth, with its restless geological activities, erases its own tracks of formation over time. Plate tectonics shift, mountains rise and fall, and erosion smooths away the past. But the moon is different. Its surface changes at a glacial pace, preserving the evidence of its birth. This stark contrast makes the moon an invaluable source for understanding the early history of our solar system. It's as if the moon has been waiting billions of years for us to read its story. One of the most intriguing aspects of this lunar story is the moon's composition, particularly its low iron content. Earth, with a heart of iron that makes up about 30% of its mass, stands in contrast to the moon, whose core is a mere fraction of its total mass. How did this come to be? The answer might lie in the violence of their shared birth. The colossal impact that is believed to have formed the moon might have vaporized lighter materials, casting them into space, while heavier elements like iron remained with Earth. But the moon's tale is not just about what it's made of. It's also about where it is and how it moves. The moon is slowly drifting away from Earth, about 1.5 inches each year. This gradual journey speaks of a past where the moon was much closer to Earth, suggesting a time when Earth spun faster on its axis. The dance of Earth and moon, through billions of years, shaped by gravity and tides, is a complex ballet that any theory of lunar formation must account for. The plot thickens when we consider the moon's two faces, the near side and the far side, each with its own unique characteristics. The near side, with its thinner crust and history rich in volcanic activity, is markedly different from the far side's thicker crust and quiet volcanic past. These differences raise questions about the moon's cooling process, its volcanic history, and how it has been shaped by the impacts of space objects. In the quest to unravel the moon's ancient secrets, scientists stand on the cusp of a new era of discovery. With humanity poised to return to the moon through the ambitious Artemis program, the anticipation is palpable. This upcoming journey isn't just a leap for space exploration. It's a gateway to a treasure trove of information that could finally answer the lingering questions about the moon's formation. For now, scientists make do with what they have: lunar samples from past missions, data from orbiters, and a growing understanding of planetary formation. These pieces of the puzzle are being meticulously analyzed, helping to build sophisticated computer models. These models are like digital time machines, allowing scientists to recreate the colossal collision that birthed the moon and Earth as we know them. They take into account various factors like the strength and density of the colliding bodies and how materials behave under extreme conditions. It's a virtual cosmos where scientists can tweak variables and observe the myriad outcomes, each one offering a glimpse into a possible past. The models are not perfect, unable to simulate every atom in such a massive event, but they offer a window into understanding how even minor changes in the conditions could lead to vastly different outcomes. The true power of these models lies in their ability to evolve with new evidence. Each piece of data, each new discovery refines these virtual scenarios, inching closer to a comprehensive model that encapsulates everything we know about the moon. The Artemis missions promise to be a turning point in this lunar detective story. Since the last Apollo mission in 1972, scientists have had decades to study the samples and data, but these have limitations. The Apollo missions explored regions near the moon's equator, primarily volcanic areas. The new missions aim to cast a wider net, targeting diverse locations like the far side of the moon and the poles. By drilling down and extracting core samples, scientists hope to uncover more layers of the moon's geological history, each layer a chapter in the moon's epic tale. These new samples and data will help refine the models, eliminate certain scenarios, and narrow down the possibilities. It's a cosmic game of Clue, where each new piece of evidence rules out certain theories and brings others into sharper focus. But there's always the thrilling potential for surprise, new discoveries that could turn our current understanding on its head. The moon, with its silent craters and ancient plains, may still hold its greatest secrets, waiting just beneath the surface for the curious hands of humanity to unearth them.